Hello all, in this lesson we're going to be studying balancing equations and we'll also add to that determining missing mass and determining missing reactants and products. There is a bookwork associated with this lesson. I want you to copy this down as a header on the second page of your Cornell notes, which will become our classwork. And under that header, please copy down this aim. How do you balance equations and solve for missing mass? And follow it with these do now questions. I'll correct the formatting now. Alright, so let's start by balancing the following equations. I'm going to go ahead and for each of these create an inventory, and I want you to do the same. So this is what I got, and I'll start balancing the first one. What I can see is that I'm going to need some extra lithium on the left-hand side, and I'm going to need an extra nitrogen on the right-hand side. I do recommend starting with nitrogen, so let's double the amount of lithium and nitrogen on the right. So that's going to give me 6 lithiums and 2 nitrogens. So my nitrogens are now up to date, but I need extra lithium on the left now. So I'm going to put a 6 in front of there, and then that'll mean I have 6 Li. So all balanced, good. Let's do the next one. I do seem to need double the amount of aluminum on the left, but it's not really going to get us anywhere. I can see that because once I double the aluminum here and then start messing with the oxygen here, it's going to change the aluminum. So I'm just going to be smart about this, and I'm going to do oxygen first. This is what I call a 2-3 issue, where you have 2 of one thing and 3 of the other. So what I recommend is to triple the oxygen on this side and double the oxygen on this side. Because if you triple this, you're going to get 6, and if you double that, you'll get 6, which is the whole point of balancing. So I'm going to go ahead and double the right-hand side and triple the left-hand side, at least for the oxygen molecule. So let me update my inventory. I now have 4 aluminum on the right and 6 oxygen. On the left, I still have 1 aluminum, but I have 6 oxygen. And I can easily fix the aluminum on the left to be 4 by putting a 4 right in front of the molecule there. All right, so the last one. I have to double the silver on the left, but for the same reason, it's probably not going to be my first move. Hydrogen could be changed, except that they're equal at the moment, and sulfur actually is equal at the moment as well. So that means I don't really have any other choice but to change silver, and I guess that means it's the only thing that needs to be fixed. So I'll put a 2 in front of the silver, and I'll update my inventory, and everything will be balanced at this point. You might be asked for the sum of the lowest whole number coefficients, and for the first one it is going to be a 9. For the second one it's going to be a 9, and for the third one it's going to be a 5. So in case that comes up as a multiple choice, that's how you do it. Alright, let's do some more. This time I'm going to put in the inventories, and I'll come back and see how you guys are doing. Okay, so I have my inventories in, and we're going to just go ahead and start. In the first one, we have a problem with aluminum, which I could fix if I need to. The sulfates look to be pretty good, except that I need 3 sulfates on the right. And the zincs look okay at the moment, and the chlorine, I have 2 on the left and I have 3 on the right. This is a 2-3 issue, so we could start there, but I'm actually thinking that a good place to start would be with either the aluminum or with the sulfate. So I'm going to start with the sulfate and then see what happens. So we'll do sulfate first. I'm going to triple the sulfate, which also triples my zinc. So now I have 3 sulfates and 3 zincs. I need to fix the zinc on the left-hand side now. So I will triple the zinc on the left. That'll give me 3 zincs, but it'll also give me 6 chlorines. And things are looking good except for the aluminum and the chlorine. I need to double my aluminum and I need to double my chlorine on the right-hand side, which is convenient since the aluminum and the chlorine are in the same compound. So I'll just put a 2 in front of that, and that will give me 2 aluminums, but it'll also give me 6 chlorines. which does in fact balance the equation. And we'll go ahead into the next one now. So carbon is always a great place to start. So let's go ahead and start with carbon since I have it in this one. Let me just multiply the carbon on the right hand side by 8. So I'll put an 8 here, and I'll update my inventory to have 8. And that's going to give me 16 oxygens here plus 1. So that is 17 oxygens. Don't panic. Let's do hydrogens next. So hydrogens, I just need to have, it looks like to octuple the hydrogens on the right. So I'll put an 8 there. That'll give me 16 hydrogens. And 8 oxygens plus 16, that's 24. So my hydrogens were at 16 and my oxygens were up to 24 at this point. So right now the carbon looks good, the hydrogen looks good, it's only the oxygen that's out of whack. And I think if I just multiply the oxygen on the left-hand side by 12, then that'll give me 24 oxygens and we'll be all set. Alright, let's do the last one. Carbon is a great place to start, so let's start there. I'm going to triple the carbon. That'll give me my 3 carbons that I need. It does mess with oxygens a bit. It's going to give me 6 oxygens, plus this one is 7 oxygens. Don't panic about that. And we'll do hydrogens next. I'm going to quadruple the hydrogen on the right-hand side, which is going to give me my 8 hydrogens, but it's also going to give me, let's see, 4 oxygens plus 6 oxygens is 10 oxygens. So instead of 7, I have 10 now. And I need to, everything looks good except for oxygen, so I'm going to pentuple the oxygen on the left to give me 10 oxygen on the left, and now we're balanced.
In this video, we are going to learn about calculating masses in reactions using 2 examples. There is an important rule in chemistry, being that the mass of a reaction is always conserved. This means that the mass of the reactants must equal the mass of the products. Let's think about this. If you combust 12 tons of coal, which is mainly carbon, with 32 tons of oxygen in a power station, you should be able to calculate the number of tons of CO2 produced. Pause the video and think about this. Continue when ready. If you said 44 tons of CO2, you'd be correct because the mass has been conserved.
So let's use what you just watched to help us answer this question. If 103 grams of potassium chlorate are decomposed to form 62.7 grams of KCl and O2 according to this equation, so here's my potassium chlorate decomposing to form potassium chloride and oxygen, to what must the mass of KClO3 be equal? So since we know that the KClO3 had a mass of 103 grams, and we also know that we have 62.7 grams of the potassium chloride being produced, and we want to know how much oxygen is being produced, it's going to be some pretty simple algebra based on the law of conservation to figure out how much oxygen that would be. But you would end up just subtracting the 103 minus the 62.7 to get 40.3 grams, and this is because of the law of conservation. So now I can see that I actually have just answered this second question. The first one I misinterpreted. To what must the mass of the KClO3 be equal? It must be equal to the mass of the KCl and the O2 combined. So the equation above did not need to be balanced, and the reason for that is because when we're dealing with masses alone, and because masses have to be conserved, then you can treat them independently of the number of moles that are represented. So it's only because mass must be conserved that we don't have to worry about the moles. All right, let's try another question. If you are given an incomplete equation and you need to find the missing reaction or product, it is possible to find it. I recommend making an inventory to determine what elements are missing from a given side of the reaction equation. So let's start now. So one of the things that's easy to see right now is that on the right-hand side of the equation, I seem to be missing 1 hydrogen. So I'm going to write that in. One of the things that's weird though is that if X right here really were a single hydrogen atom, it wouldn't make a lot of sense. And that's because hydrogen is an example of a diatomic atom, so it would only appear in its diatomic state, which means that the equation would actually look more like this. Which brings up another problem. If we have two H's here instead of one, then our equation is no longer balanced. So what we should do is balance this equation. So here's my inventory. My first suggestion is to actually double the hydrogen that's inside the sodium hydroxide. Because what I'm going to try to do here is I'm actually going to try to take care of the hydrogen by making them both a 4. And I think I can do that by putting a 2 here and a 2 here. Let's see what happens. So it changed several things. It did give me the 4 hydrogens that I wanted, but it also gave me 2 oxygens on the left, so those are here. And it changed the sodium, the oxygen, and the hydrogen when I doubled the sodium hydroxide. So that gave me 2 sodiums, it gave me 2 oxygens, and for the hydrogens I already had 2, so it's 2 plus 2, or 4. So at this point we're almost all the way balanced except for the sodium. And we just need to put a 2 in front of the sodium on the left-hand side, and then we'll have our equation completely balanced at 2, 2, 1, 2. So when I answer the following questions, what's missing from the unbalanced equation, I would say that we had 1 hydrogen atom missing. And now that we've balanced the equation, I would say that there is nothing missing. Okay, so we've reached the pair up. I just want you to copy down these questions and we'll work on these in class tomorrow. And same thing for this summary, copy them down and we'll work on them tomorrow in class. Thank you for watching.